Hey guys, Rob Skiba here. So it's taken me a whole lot longer than I thought it would to get the extended version of the Chicago Skyline video done, mainly because I've had a whole lot of other stuff I've had to get done and been working on a lot of other projects and traveling and doing conferences and stuff like that. I've still been plugging away at this, just a little bit here, a little bit there. But wow, the more I do, the more I realize there's more to be done, and the more I say, I realize there's more to be said. This video is already several hours long. I've been working on this for about 7 months now, and so a lot of what you're going to hear was actually recorded in 2016. I'm now picking the project back up again in 2017, and I've decided to just divide this up into multiple parts. That way I can at least get some of the content out as I finish it in durations of an hour or less. Now, I've already been releasing bits and pieces of this video in short chunks on YouTube, but this is the elaborated version from which those were derived. So this was going to be part one, and I call it Refraction, Magnification, or Curvature. And it's going to deal with the issue of, are we looking at looming? Are we looking at atmospheric lensing? What is the deal with the Chicago skyline? So I'm going to use this video to sort of lay the groundwork for the videos that will follow. Again, all this is an elaboration on the Rob Skiba Proves the Chicago Skyline is Not a Mirage video, which was basically just a half-hour highlight video of the trip, just really giving a high-level view of what we did. The series I'm working on now is going to really elaborate on a whole lot of things and help to explain my ultimate conclusions after that trip. And we did that trip back in June of 2016. Over the weekend. It was my birthday weekend, actually. Went out with Rick Hummer to go on Lake Michigan and determine whether or not the Chicago skyline, as viewed from the other side of Lake Michigan, was in fact a mirage or not. And that, of course, came as a result of seeing this news report in April of 2015.
This is from Joshua Nowicki, and what you're seeing here is a mirage. We typically would not be able to see this from the Lake Michigan shore. We talked about this last night. Conditions are right on the lake that we're actually seeing a mirage of the Chicago skyline. Very interesting here. Here's what's happening. This is a good example of a superior mirage. So Joshua was on the Lake Michigan shore. He was looking towards the west, and Chicago's beyond the horizon. Should not be able to see it. However, with the right conditions, we have an inversion. We have cold air near the cold lake water and some relatively warmer air above it. This will bend the image of that skyline back towards the viewer. And so typically we would not be able to see this. This image would be viewable from much, much higher in the sky, up in space. But instead, we're able to see it on the Lake Michigan shore.
Now, when I first saw that, I immediately, just looking at the picture, I'm like, there is no way that is a mirage. And Rick was saying, definitely not, that he's lived in that area his whole life, and he actually got in trouble in school for saying that he could see Chicago from the other side of Lake Michigan. And because that goes against what we're told about the ball. You can't see over the curve, you know. So because Joshua Nowicki was able to see the Chicago skyline from the state park that he was in, and by the way, he was at about, I believe the elevation was about 200 feet. And he was somewhere in the vicinity of about 53 miles away, according to the Channel 57 news report. And depending on where he was in the park, looking toward the west, he was looking on a heading of about 260 degrees to the west. We were not able to get that far north where that park was to charter a boat from that area. We were only able to charter a boat from a company that was further south in New Buffalo. But from where we were, looking on Google Earth, the distance that I saw on Google Earth was 46 miles. Most of the people I talked to there said 42, so I'm not sure what the discrepancy is, but after watching the captain of our boat plot it, it looked like he was zoomed way out, and they may be plotting to some location just off the shore. But at any rate, if you go to the beach where we were, or the mouth of the harbor where we just pulled out and saw the city initially from, that distance from that location directly to the Willis or the Sears Tower is almost exactly 46 miles. So, you know, Joshua Nowicki's at 53 miles. We're at 46 miles. I really didn't think 7 miles was going to make that big of a difference, especially considering the fact that he was at an altitude of at least 200 feet, and our camera level was about 3 feet off the water. So, 3 feet versus 200 feet and 46 miles versus 53 miles. All said and done, it seemed like a very reasonable comparative test to perform. So that's what we did. Regardless, when we looked at that, we're like, that is not a mirage. And so our primary goal and our objective, as stated in the video that I played before, was to determine whether or not it was a mirage. It's funny how many comments I got, however, about people going, congratulations, Rob, you just proved the world's a globe. And, people were taking screenshots of my video and stuff like that. I'm like, did you guys even watch this video? Did you even look at the title? My primary objective was only to show that it's not a mirage. Now, to be fair, I was hoping to see some other evidence regarding the flat Earth issue as well. So this video will deal with both the mirage issue as well as the issue of globe versus flat. Now, I wasn't the only person who questioned the Chicago Skyline picture, whether or not it was a mirage. Lots of other people out there in the internet community looked at that and said, that's a bunch of garbage, that is not a mirage. And one of them was a guy named Rich from the YouTube channel Mr. Thrive and Survive. And I'm just going to play a clip here from a video he did after he saw my highlight video of the Chicago Skyline. He did a little bit of a commentary, and from his background, he gave his analysis as to why he didn't believe that it was a mirage, and how that it was actually that picture that got him interested in this whole flat Earth discussion to begin with.
Rob Skiba recently, I'm sure with his own money and with the money of a friend of his, went and flew to the Lake Michigan area, and on their own time and money, and went out to debunk this right here, which is what got me into flat Earth in the first place. This picture right here of the Chicago skyline, and the mainstream media's lame expression that this was, or contention I should say, that this was a superior mirage. And most of you guys know my history as a weatherman and different things like that. I've taken thousands of at-sea observations and know what a superior mirage looks like, know what it does not look like. And there wasn't one aspect, not only visually, that was a superior mirage in that photograph, but the atmospheric conditions absolutely were not correct for a superior mirage, and also for the depth of the projection of that mirage. For it to be a mirage and be projected like that would be in the magnitude of a 5,000 foot deep, roughly. Okay, I'm going to show it. The inverted image must first be lifted 2,400 feet and then inverted. This is how it would work, guys. And I'm going to show you how they showed this, but didn't show you the height because they show you how ridiculous it was. So after it's inverted, this is what the superior mirage would look like. This upside down thing here at 4,800 feet. But no, that is not what we saw, is it? No, we saw it rectified up. So to rectify it up, you have to add another 2,400 feet to get to look the way it did on the surface. Not to mention the water line also had to go all the way up there with it as well. So we got 5,200 feet here. That'd be the world's deepest inversion from the surface I'd ever seen. Now, just to show you that the weatherman did that, let's take a look at that. Okay, I've inserted the image of the weatherman. Now let me do this a little bit slower. Okay, let's take this down. So here we have the original from the shore looking out, if it wasn't a mirage, correct? This is what we know to be the truth. You would have to invert it, which is exactly what he shows here. He shows a ship right up, right side up, then it goes upside down, then you got to flip it up again just like I did, and then you got to raise it up one more time just like I did, because it has to be put right back up again. See, what they're not showing you is the ridiculousness of how high this mirage would be. But I'm showing you what it is right here. And remember, since we saw the water line the whole way, okay, let me show you how that would look. The water was up there with it too. So from the guy that took the camera all the way out, okay, we're supposed to believe that there was a continuous 5,200 feet inversion that suddenly just happened to come down to the guy right on the edge perfectly, so that he saw, when he looked out, like a perfect skyline across there of Chicago. So again, here are the steps. You have the regular upside, right side up image, then you turn it upside down. It has to happen on a mirage, guys. This is the typical one you see out at sea, this upside down one right here. Now what they're claiming is it was so deep, this layer here, this inversion, that it had enough to rectify back up once again. 5,200 feet. Now why did I come up with that number? Because the curvature from the distance would be 2,400 feet roughly from 60 miles. So if it happened to get the exact perfect curvature from the top of these towers, okay, it will require a minimum. Actually, it requires more than this. I'm being generous. It requires 2,400 feet plus the height of the tower. It would be 2,400 feet just to get the base. So I'm not even including that. What's the height of the tower? I don't know, whatever that is. So many, is it 1,000 feet, 1,200 feet, 14? I don't know what it is. But that's really that times 3, not 2,400. I'm being very generous. So if we were to, you've probably seen, look up superior mirages. You'll find like ships that will be upside down looking, one on top of the other. That's the typical superior mirage, which you would see right here. Okay? That would be a minimum of 4,800 feet. But since the image was not inverted and right side up, which really tells you you're looking at Chicago, you're not looking at a superior mirage. Okay? It requires 5,200 feet. I implore you, please call any National Weather Service office and ask them if they've ever seen an inversion from the surface up to 5,200 feet. Actually, then you'd have to have the height again. Even I've taken the height of the buildings out the whole way. To get it rectified back up, you'd have to add the height of the buildings. Let's say it's 1,500 feet, because we're seeing well above the buildings here. Above the Sears Tower over here, we're still seeing that. So, mile and a half. Ask them if they've ever seen anywhere a balloon launch that had a mile and a half from the surface all the way up to there, an inversion. Okay? They're going to laugh at you.
All right, yes. I did finance the trip myself. I spent the better part of a year saving up for it. I bought the Nikon Coolpix P900 specifically for the purpose of doing that test. Wasn't able to do it when I wanted to back in 2015, so I started doing some other things with that camera, which I'll show you in this video also. But between the airfare and rental car and hotel room and additional supplies and, of course, chartering the boat ride, all said and done, the trip costs about $2,500. So, yeah, I went out there on my own dime to try to figure this out. And you'll note also, this is the picture that the weatherman had on his screen showing how the mirage works. And, I mean, look at this bottom sailboat. Then it gets inverted, and then it gets flipped again, and then they got a higher one up here. Now, I mean, go back and rewind the video that Mr. Thrive and Survive did, and think about how crazy that is with regard to the entire Chicago skyline. All right? I mean, you have to believe that this entire city was thrown up into the sky, and perfectly symmetrical, straight up and down, clean lines, and all that stuff. But it's important to point out that before we even did our trip in June of 2016, that the weatherman actually did a special on the 1 year anniversary of being sent that picture from Joshua Nowicki and doing that initial report on it. He actually debunked himself. He had already done a video basically saying, okay, it's not a mirage, it's something else. Here's the video that he did in April of 2016, 1 year after the initial story.
All right, 1 year ago to this very night, I received this picture. After showing it a year later, I received email after email after email saying that this was not a mirage. So I climbed the dunes myself to see this phenomena and spoke with the experts to settle this skyline skepticism. Joshua Nowicki captures it all through a lens. A year ago, I showed this amazing picture on air and online. The story has been one of the most viewed stories on our website ever. Most click because of its rarity, and also because there are Skyline skeptics. They say my explanation is a cover-up. A cover-up to their belief that this picture is proof the Earth is flat. Here on the shores of Lake Michigan at Warren Dunes State Park, just 50 miles towards our west is Chicago. However, we can't see the skyline, at least from this vantage point.
Earlier this year, there was a really good chance. It looked like probably 40 or 50 buildings looked visible from the top of the dune over here, which is the most I have ever had a chance to see it.
Is it evidence of early philosophers that the world isn't round? Or is it a mirage?
If you follow this right here, it's really easy, right through here.
We climb the dunes to find out.
A mirage is a case of atmospheric refraction, and it's caused by the fact that you have temperature variations in the atmosphere, and these cause density variations.
Dr. Mark Rennie is an associate professor of aerooptics at the University of Notre Dame.
So literally the speed of light varies within the air, and this variation of the speed of light has the effect of bending light rays.
Sometimes the Lake Michigan waters makes us see things. Here we are at the top of Warren Dunes. Pretty exciting as the inversion is setting up as we speak. A spring night, the lake waters are still very cold. And we can see out on the horizon and above it a dark line that's starting to show up just above. That's the inversion. That's where temperatures are different below than they are above and creating that cap. And we're beginning to see that atmospheric lensing, where in spots along the horizon we're seeing either breaks in the buildings or where the buildings may be flipped or a distortion caused by the mirage or atmospheric conditions that are changing as we speak.
What's happening is the light from Chicago is being bent by the cold air above Lake Michigan slightly downwards towards the observer here in Michigan. And that's helping the light rays get around the curvature of the Earth, so to speak, so that Chicago can be seen almost all the way down to ground level.
Let's hear that again.
What's happening is the light from Chicago is being bent by the cold air above Lake Michigan slightly downwards towards the observer here in Michigan, and that's helping the light rays get around the curvature of the Earth, so to speak, so that Chicago can be seen almost all the way down to ground level.
See, now there's buildings shown up straight ahead of us. But if it is a mirage, argues many of the biggest critics who've emailed me, the image should be upside down.
The word mirage originates from the same root word as the word mirror. So technically, I think if you're going to be a stickler about it, you would say a mirage has to have an inverted image. But again, the physics is all the same.
The science is the same of that of a lens. Here's a simple example.
So if you're looking at Chicago here, now you can just see the top of the Sears Tower, and if our simulated temperature inversion moves into place, hopefully now you can see pretty much all of Chicago,
see all the lower buildings,
including what's at ground level.
So the atmosphere really is acting like a lens.
Yes. So this is, if anything, this is definitely a demonstration that refraction displaces the image, and basically where you think the image is not where it actually is.
That now infamous picture from a year ago, that's looming, as are these photos that we snapped. This is a mirage. We caught this looking towards Michigan City. Notice the distortion or flip in the image in the time lapse. On a normal day, say in the summer, you can see Chicago, but only a dozen or so of the tallest buildings.
Anything more than that, especially once you get over 10 or 12, something's happening, because that's not usually there.
The views along the lake are always changing, along with the weather.
It's always different. It's so unpredictable that I want to catch as many different views of it that I can.
So technically speaking, this pic is looming. It's not a mirage, but that's all semantics. It's all atmospheric refraction. Now, we have a lot of web extras with this story. Log on to abc57.com after this newscast. You can see the time lapse, a short lecture by Dr. Rennie, and how you can calculate how far you can see to the horizon based on your location. Reporting live, I'm Chief Meteorologist Tom Coombs.
And you can learn more about the story from the Channel 57 News website under the Skyline Skepticism, the Lake Michigan Mirage story. Now, let me just say, guys, stop writing to this poor weatherman and going off on him. I mean, look, the guy, I mean, I feel sorry for the guy. I have nothing against him. I just, I didn't believe what he was saying. He had no idea that his little news blurb before doing the weather report was going to stir up as much of a controversy as it did. Probably wasn't even aware that there even was a discussion online about flat Earth of all things. All right. Now, this is the part right here on the website. It talks about the Warren Dunes State Park is about 53 miles across the lake to Chicago. And someone that's 6 feet tall standing on the lake shore can only see about 3 miles to the horizon. If you climb to the top of Tower Hill, 250 feet, you can see almost 20 miles to the horizon. That's still not far enough to see Chicago, at least at ground level. The Willis Sears Tower is 1,450 feet to the top. Doing the same calculations, you could see it from up to 65 miles away on Tower Hill. That day on the shores of Lake Michigan at Warren Dunes State Park, just 50-some miles to the west, Chicago was hard to see on the slightly overcast day. So what's really bizarre about this story is you've got Joshua Nowicki, who's a semi-professional photographer, and this weatherman looking out there, and they are seeing distortions. I mean, no question. The weather causes atmospheric distortion, and it does cause mirages. But they seem to be of the opinion that the more buildings of the city that you can see clearly, the more we're dealing with atmospheric conditions. And yeah, look, I'm not a meteorologist. I didn't go to school for any of this stuff, but common sense says to me anyway that no, the default is probably to be able to see the city. But when we can't see the city, it's because of atmospheric conditions, atmospheric blocking, atmospheric, distortions causing mirages and things like that. So in other words, we should be able to see it. It's when we can't see it that we're dealing with atmospheric conditions. These guys are saying, oh, when the conditions are just right, the atmosphere acts like a lens. And I pointed out in the video there in the text I put on the side, keep in mind the phrase atmospheric lensing and looming. And so here we see the difference between looming on the left and a mirage on the right. Both of these pictures were taken by Joshua Nowicki on April 13th. And he's got, you could actually watch on that website, they got a time lapse showing, he over a period of time, Joshua kept the camera pointed towards Chicago, and sometimes you can see it, sometimes you can't. And I contend that when you can't see it, it's because of the atmospheric blocking and various conditions obscuring it. When you can see it, it's when you have a lack of atmospheric conditions. I don't believe we're dealing with some kind of magic where it's going, beaming the city over the curve so that we can see it perfectly. Now, looming is defined by the dictionary.com website as a mirage in which objects below the horizon seem to be raised above their true positions, and also to appear indistinctly coming into view in indistinct and enlarged form. Well, the indistinct part's tripping me up here because everything was very distinct. I mean, straight lines, perfect. And interestingly enough, speaking of the dictionary definition of looming, I showed dictionary.com earlier, but I also looked up the definition of looming on Wikipedia and found some interesting things here that may support what I just said. For instance, this last paragraph here says, there is a different type of mirage that is also described as looming, in which distant objects appear much nearer than they actually are. Is explained in the same way as the image of the ship, except that the image is not inverted. The density variations may also act as a magnifying glass. And if you click on the link above where it says for the atmospheric refraction phenomena, see looming and similar refraction phenomena, you come to this page. And it says, while mirages are the best known atmospheric refraction phenomena, looming and similar refraction phenomena do not produce mirages. Mirages show an extra image or images of the miraged object, while looming, towering, stooping, and sinking do not. No inverted image is present in those phenomena either. Depending on atmospheric conditions, the objects can appear to be elevated or lowered, stretched or stooped. These phenomena can occur together, changing the appearance of different parts of the objects in different ways. Sometimes these phenomena can occur together with a true mirage. And it goes on to say, looming is the most noticeable and most often observed of these phenomena. It is an abnormally large refraction of the object that increases the apparent elevation of the distant objects and sometimes allows an observer to see objects that are located below the horizon under normal conditions. And they have this picture here, and if you click on that, it says the distant boats appear to be floating in the sky as a result of looming and other refraction phenomena. I'm going to have to disagree with that. I think all that's happening right here is you're actually seeing the ships where they are. Now, they may be enlarged a little bit due to refraction and magnification and whatnot, but they're not floating in the sky. I have seen with my own observations using the Nikon Coolpix P900 that there's what appears to be the hard line of the horizon on water, and then there's a miraged horizon beyond that that you can actually watch boats go right out into. And you've seen that online before with the Red Boat, for instance, that video done by Lori Ferrari. And I also did a similar video where I went to Florida and I was visiting my family. We went out to the beach, and it was a fairly clear night, although it looks a little bit hazy in this video here. And I was watching ships go out to sea. And these ships right here that you see on the screen started out right beside me, and I watched them leave the dock and go all the way out to where you see them right here. And I just kept the camera on them and just followed them out there. You'll see the hard line right here of the water, and that's about 2 to 3 miles out, I'm guessing. But if you just keep watching, they'll go beyond that line. You'll see them going out beyond the hard line right there. And here's a shot where they've gone way beyond that line. They're out at between 4 and 5 miles right now. And looking at the curvature chart, at the water level, you should be missing 10 feet of the ship. And my camera was just about 2 to 3 feet at the most above water level, and I don't see anything missing there. So I believe all that's happening right there is just like when you look out at cars driving on the highway and it look like there's a big puddle up ahead, but it's not. It's just miraging on the ground, making it look like water. And so in this case, out to sea, it blends in with the sky and it gives the appearance of losing the horizon, but you haven't. The ships will just keep going out on that water. It's not a mirage, it's not looming, it's not anything. It's just ships going straight out to sea on a flat level surface. Now, I need to point out the fact that there is a lot of water in the atmosphere. And biblically speaking, it's also kind of interesting that the heavens, and we know that there are multiple heavens. Many say that the first heaven is where the birds fly, and the second heaven is space, and third heaven is where God is, and perhaps there's even more heavens within the heaven that God's in. But the word heaven in Hebrew is shamayim. And if you look that word up, like on Bible.cc, for instance, it's Strong's number 8064, shamayim, heaven. Scroll down, gives you a little bit more definition here from Strong's exhaustive concordance, air, astrologer, heavens. It's a dual of an unused singular, shama, from an unused root meaning to be lofty, the sky as aloft. The dual perhaps alluding to the visible arc in which the clouds move, as well as to the higher ether where the celestial bodies revolve. So it's lofty, it's up there. And so that would be the singular. But it's like a compound word, because within the word shamayim is the word ma'im, and that's Strong's number 4325, and that's the word for water. And if you scroll down to the Strong's Exhaustive Concordance elaborated definition here, water, wasting, watering, course, dual of a primitive noun but used in a singular sense. Water, figuratively, juice, by euphemism, urine, semen, piss, wasting, watering, coursing, flood, spring. And I believe it was a lecture that was done by Dr. Kent Hovind where I first heard this, but the word shamayim could be understood to mean water in it. And there certainly is a lot of water in the heavens, or what we call the atmosphere. So I went to a few websites. I just did a Google how much water is in the atmosphere, and this is the USGS website, usgs.gov, Science for a Changing World. The USGS Water Science School talks about there is always water in the atmosphere. Clouds are, of course, the most visible manifestation of atmospheric water, but even clear air contains water in particles that are too small to be seen. One estimate of the volume of water in the atmosphere at any one time is about 3,100 cubic miles, or 12,900 cubic kilometers. And it goes on to say that if all the water that's in the atmosphere were to rain down at once, it would cover the globe to a depth of about 1 inch. And this is confirmed on a number of websites, but I'll just show you one more just for the sake of argument here. This is the Y Files, the science behind the news. They have an article, How Much Water is in the Atmosphere. It says, at any moment, the atmosphere contains an astounding 37.5 million billion gallons of water in the invisible vapor phase. This is enough water to cover the entire Earth, land and ocean, with 1 inch of rain. And, of course, goes on to talk about that as well. So, yeah, there's a lot of water in the atmosphere. I think we all kind of just know that, but I don't think we've ever really thought about what that means. And so I'm thinking if the atmosphere, especially over water, is made up of zillions and zillions of tiny convex drops of water, then collectively perhaps they all combine to make one big convex lens, in which case it would act like a magnifying glass. Okay, so with that in mind, let's look up some websites dealing with the refraction of light. You might see a graphic, something like this, showing light bending downward. And here's your typical graphic showing how light rays entering some sort of medium, like in this case water, refraction causes the light to bend downward. Now we've all seen pictures of, a pencil or something in a glass of water, and how not only does refraction bend the image downward, it also magnifies it. I'm going to say that again. Water causes refraction, bending the image downward, and magnifies it. So this is important now. But they have sort of an unusual, although I would say very common, view as to how downward refraction is being used to allow us to see things up, over, and around the curve. And while I was looking at the Channel 57 News website, I found some raw footage, it looks like, of the conversation the weatherman had with the optics expert at that university. Check this out.
One way that can happen is called looming, and this is a situation where cases where you can see objects in the distance that would normally be obscured by the curvature of the Earth. So as an example, in the next picture we'll show a picture taken from a person standing on the shoreline of Lake Michigan, and he can see almost to ground level Chicago, whereas normally you wouldn't be able to see that far because of the curvature of the Earth. So what's happening in this case is, especially this time of year, Lake Michigan is much colder than the air above it, and that has the effect of cooling the air just above the lake. And so now you have the case where the index of refraction is increasing with the height above the lake, and this has the effect of bending light rays back down so that they can get around the curvature of the Earth and be seen by an observer standing on the shoreline here in Michigan.
Now, prior to doing this research, I probably would have just shook my head and agreed with everything you just said, but now that I've begun to question the shape and nature of the Earth and look at it from a different perspective, this seems to me like an ad hoc theory. It seems like they start with the premise, well, we all, of course, know the Earth is a globe, it's a sphere, and Chicago's too far away for us to see it, so therefore this must be what's happening. And they create a nice graphic and take the principles that we know and understand about refraction and how the atmosphere plays into all that, and throw together again, it looks to me now like an ad hoc theory to explain how the city is thrown up over the curve so that we can see it on the other side of Lake Michigan. That's what it looks like to me anyway. All right, let's continue.
So is all this under mirage and then looming is under mirage, or what are the semantics of looming versus mirage?
Okay, well, that's all. I guess that's all in the details of the terminology. From what I understand, technically, I think mirage has to have an inverted image, whereas there are other atmospheric effects such as looming or towering that are purely displacement, and you don't necessarily have to have an inverted image in order for refractive effects to occur in the atmosphere.
So they would all fall under the category of atmospheric refraction.
I guess that would be a good thing to say. Yes.
Okay, so again, this is their graphic. According to them, we know the Earth's a ball, so therefore this is the way it's working. Chicago's over here on the left, we got the curve of the Earth here, and the light rays, which would normally be going straight across, have to be bent due to the atmospheric lensing, the density of the atmosphere and whatnot, causing the light to refract downward, basically just conveniently enough over the top of the bulge of the curve so that we can see it on the other side. Now, here's where I would differ with this whole idea. Again, just sort of flipping the board. Let's just say we don't start with any preconceived notions of the Earth as a globe. Let's entertain for a moment the completely absurd notion that water is flat and it always seeks its own level. And we're looking across a flat plane of water, 46 miles across. Check this image out right here. Now, I caught this image shortly after Rick and I returned from our trip across the lake. We grabbed a bite to eat, and then we went out to the beach, and it was still clear out, so we got the camera out and looked 46 miles across the lake to see this right here. This image is extraordinary. Okay, the boat right here, I'm going to guess, is less than a mile away. And I base that because these people walking in front of the camera here are walking across some rocks that sort of jut out and kind of fence in the harbor area. And they are only about a quarter of a mile away from where we were when I shot this. I shot this image from right about here. This is where we were looking across, and this is the area right here where those people were walking. And the boat, as you could tell by the size of the people on the boat, wasn't too much further beyond that. So maybe a half mile to a mile, or at the most, I would say, away from where we were. All right, now when I was headed back to Chicago to catch my flight, I snapped this picture of the Willis Tower. And this is, if you go on Google Earth, this is right about the area right here where I believe I was when I took that picture. Looking across, it's only about 0.6 of a mile. So I'm just a little over a half mile away, and look at the size of the tower as compared to the car that was diagonally in front of me. We were looking at the Willis Tower from this direction right here when we were on the other side of the lake. Now, okay, so let me slide the car over and shrink it down to the appropriate scale beside the boat. Do you see something rather interesting here? This building is significantly magnified. The image on the left shows the size and scale of the building next to a car at 0.6 of a mile away. The image on the right shows the same building and the same car with a boat at 46 miles away. The atmosphere really is acting like a lens. What type of lens? A convex lens or a magnifying glass. So I'm going to suggest this is what's happening. The atmosphere is acting like a lens, which magnifies the city, brings it up a little closer, and as it does so, we start to lose a little bit of the bottom of the buildings, and perhaps due to the density in the atmosphere, there's additional refraction that takes place that makes it drop down even more. Is that what happened? Let's look at it from another angle here, from the side view. I'll bring our graphic back in of refraction. Let's go ahead and orient the graphic so it better represents what we're looking at here. I'll angle the light rays to show the density of the air here causing the refraction, and bring our lens in so we can magnify the city. It brings the city up, and as it does so, we start to lose a little bit of the bottom of the city, and perhaps either due to the magnification or due to additional refraction, maybe it is dropped down a little bit more, and this is what we end up with. Huh. Just like we saw. Now this is a still frame from the half-hour video that I did, and the numbers you see there are all based on the numbers that Tony was giving me based on his device. His device said it was 37 nautical miles, which is 42.6 statute miles, but when you plot the same exact location that we were at, the exact distance you get on Google Earth is 46 miles. So you basically add about 4 miles to all the numbers that you saw in the half-hour video. But here's where it gets interesting, at least to me. Both of these pictures were taken with the same camera. Now, if you remember from the half-hour Chicago Skyline video, I was saying I can see Chicago. We're about 42 miles away. I can see it. The problem is trying to get the camera's having trouble focusing on it because it's moving up and down and it's so zoomed in. But I can totally see it. Rick was not zoomed all the way in. He was using my camera, the Nikon Coolpix P900, but he was only zoomed in about halfway when he grabbed the shot above. Now I know that when I got the image below, I was zoomed all the way in. And so some people may point to one of my videos where I was actually debunking myself. If you remember that NASA video showing the Earth and the Moon, and the moon was going in front of the Earth. So I did a little experiment where I used a baseball as a moon and a larger ball as the Earth. And I got at the end of a long hallway with my Canon 70D and zoom lens, and zoomed all the way in on it. And this was the image that I captured doing this experiment. There's the NASA image on top, and there's my image. And so, you know, just by virtue of the lens, it does magnify the distant object to make it look proportionately large to the object that is closer to you. So is that what's happening here? Well, both these images were shot from the harbor area here. The red line at the top is where we were in the boat. We're just about to depart when I asked Tony to stop, and I got the camera out to shoot Chicago. And the lower red line is where we were on the beach when I took the picture on the bottom there. So, and the distance between those two locations is less than a quarter of a mile. So it's negligible. We're still looking about 46 miles across either way. Now, here's the shot from the beach before I zoomed in. Now I'm zooming in, and I'm going to stop it right about here. That's about halfway on the zoom, and I believe that's where Rick had the camera set when he took the picture above. Based on the size of the building right here, I'm going to guess that he was about halfway. Alright, so let's go ahead and continue the zoom. And this is zoomed all the way in. The Nikon Coolpix P900 has an 83 power optical zoom, and that little punch in after that was the digital zoom afterward. It has a digital zoom that goes beyond the 83 power. I did not go all the way in with that. I just punched it a little bit because I wanted to frame it with the ship right there. So that's 83 power plus. So gonna guess it's probably the equivalent of about maybe 90 power zoom or so right here. Now let's bring the picture in from the halfway zoom, and I'm going to go ahead and bring our car back in and slide the picture in from Chicago, and I'm going to scale the car to the appropriate size to the boat right here and go ahead and slide the car over to the building. So this is what the car and the building look like at half zoom. So let's try something else here. I'm going to unfreeze the video and back it off so it goes backwards, and we're zooming out back to the shoreline. And now I'm going to bring it forward again And let's see, right about here is where we have some fairly decent resolution where you can still make out the building. I'm going to zoom in here with the computer. This is a computer zoom now on this still image. And I'm going to bring the other image in from the half zoom and scale the car over to the digitally zoomed in image of the almost completely zoomed out shot. And so you got three different zooms here. One almost completely zoomed out, one zoomed about halfway on an 83 power optical zoom lens, and the one on the right, of course, all the way zoomed in with a little touch of digital zoom on top of that in the camera. And when looking at these images compared to the one on the left, which is just shot with my iPhone, I got to tell you, it looks like it's being magnified to me. Especially when you consider the fact that that building is like 45 miles away from that boat. It's 45 miles away. So, looks like there's some serious magnification going on here. And, you know, some of that could be due to the lens, I'll give you that. But I also know what I could see with my own eyes. Now, I understand you may not want to take my word for it, so all I can say is go up there and do it yourself. But based on what I saw with my own eyes, as well as what the quote-unquote experts had to say regarding how the atmosphere can act like a magnifying glass, I'm still going to go with it as being magnified. Again, you can go out there and test it for yourself. But remember, let's just go back and hear from the experts once again about what they say is happening.
The science is the same of that of a lens. Here's a simple example.
So if you're looking at Chicago here, just maybe now you can just see the top of the Sears Tower, and if our simulated temperature inversion moves into place, hopefully now you can see pretty much all of Chicago,
see all the lower buildings,
including what's at ground level.
So the atmosphere really is acting like a lens.
Yes.
So the atmosphere really is acting like a lens, according to the experts. Now, you guys don't need to go out and spend tens of thousands of dollars to get that pretty piece of paper to hang up on the I Love Me wall and put letters after your name so that you can call yourself an expert. You can be an expert with what you see here on the screen. Yep, believe it or not. Go to Walmart, and your advanced degree in atmospheric lensing technology will cost you just a couple dollars. You can get a 2x power lens for about $1.85, I think, at Walmart. Get yourself some Scotch tape. Then if you look in the description below, you'll see I put a PNG file of a city. You can print that up, cut it out so it looks something like this, what you see on the screen here. Then find a table and a chair. And okay, you're going to bend the paper so it looks something like this. Tape the lens to the table, get a chair that's about the same height as the edge of the table. Put your iPhone on the end of the chair, and the chair will act as a dolly, so you can just kind of pull the chair back. And looky here. Look what happens with atmospheric lensing. Wow, isn't that amazing? And you didn't have to go to college either. Now, you can get in a boat and drive to Chicago, and wow, look at that. Now, let's compare. See? Look at this. This is how much of the city was lost simply due to atmospheric lensing. Now remember, the experts, the guys that spent tens of thousands of dollars to get advanced degrees in this stuff so that people would recognize that they're smart, they told you the science really is that of a lens. Now, of course, the first time I posted something like this on YouTube, the baltards came out from under every rock on this plane to make fun of me and say I didn't know what I was talking about with refraction. That's not how it works, and blah, blah, blah. And they looked at the image on the lower right here of the magnifying glass showing the city and how it was all wavy and distorted. And they said, well, look, your magnifying glass made everything distorted, and Joshua Nowicki's picture was straight up and down. You're an idiot, blah, blah, blah. Well, yeah, okay, so then these other guys came out and they started posting all this stuff about the Toronto skyline. And you've probably seen the meme being passed around on Facebook and everything, showing the lower portion of one of the tall buildings there in Toronto being missing, and they're saying, see, this is proof of the globe. And you start seeing videos like this one.
Another way to demonstrate the curve is with distant city skylines. A good example is the city of Toronto, viewed from across Lake Ontario. The city is dominated by the distinctive CN Tower, currently the third tallest tower in the world at 1,815 feet. There are many pictures online of the Toronto skyline, viewed from Niagara-on-the-Lake, New York, 30 miles away. With the metabunk calculation, we see that 486 feet of the tower, or about 26% of it, should be hidden behind the curve of the Earth from that distance. And this is exactly what we see, as you can easily tell when compared to an image of the full tower at the same scale. One example they use is the Chicago skyline seen from 60 miles away across Lake Michigan. At a viewing height of 6 feet, we calculate that 2,166 feet should be below the horizon at 60 miles. So they are right that the entire city of Chicago should be completely hidden. And it is hidden nearly all the time, but sometimes it can be seen from that far away, due to a type of atmospheric light refraction phenomenon called a superior mirage. A superior mirage is caused by colder air below warmer air, which bends the light around the curve of the Earth. This event sometimes makes the news for the very reason that it is a rare occurrence.
Now, in most social settings, such a continuous condescending tone would likely get you punched in the face repeatedly, but beyond that, I have to remind you of the response that another former weatherman gave regarding the whole idea of this being a superior mirage. Let me play that for you again.
See, what they're not showing you is the ridiculousness of how high this mirage would be. But I'm showing you what it is right here. And remember, since we saw the water line the whole way, okay, let me show you how that would look. The water was up there with it too. So from the guy that took the camera all the way out, okay, we're supposed to believe that there was a continuous 5,200 feet inversion that suddenly just happened to come down to the guy right on the edge perfectly, so that he saw, when he looked out, like a perfect skyline across there of Chicago. So again, here are the steps. You have the regular right side up image, then you turn it upside down. It has to happen on a mirage, guys. This is the typical one you see out at sea, this upside down one right here. Now what they're claiming is it was so deep, this layer here, this inversion, that it had enough to rectify back up once again, 5,200 feet. So if we were to, you've probably seen, look up superior mirages. You'll find like ships that will be upside down looking, one on top of the other. That's the typical superior mirage, which you would see right here. Okay? That would be a minimum of 4,800 feet. But since the image was not inverted and right side up, which really tells you you're looking at Chicago, you're not looking at a superior mirage. Okay? It requires 5,200 feet. I implore you, please call any National Weather Service office and ask them if they've ever seen an inversion from the surface up to 5,200 feet. Okay? They're going to laugh at you.
Now let's go back to Captain Baldhard.
You can tell that it's a mirage because there is lots of distortion. The Willis Tower on the left is clearly elongated. And also, there are videos of this same view that show the buildings dancing around, changing shape, and even disappearing. Even though this is a mirage, the bottom parts of the buildings are clearly still obscured from view, just as we expect. If the Earth was flat, you could see the buildings on any clear day, not just rarely when the conditions are right for refraction. Flat Earthers use these rare events to try to prove the Earth is flat, but that makes no sense. It's called cherry picking, a favorite trick of all types of science deniers. You don't get to pick the anomalies that seem to agree with your views and ignore the common observations that don't, and still call yourself an honest investigator. That is intellectually dishonest.
Now let's see who's going to pick and choose what common observations they're going to accept and or ignore. Here's an interesting video I saw online regarding a full day time lapse revealing superior mirages. Now, this is quite extraordinary, actually. This is from skunkbayweather.com, September 7th, 2012. Notice the buildings and the shoreline here over on the left. Keep your eye on that. Just watch that, and the mountain in the background. Everything's pretty cool. You can see pretty much everything there, but as the day progresses, and we are now at 9:30 a.m. and it's 59 degrees, 60 degrees, it's getting warmer, the temperature is changing, we start to see some miraging take place, right? It starts to distort things a little bit. Ooh, look at that. The water seems like it's getting higher, and we're losing buildings, and we're losing the beach. Here it is now, noon, 63 degrees and climbing. Uh-oh, there it goes. Oh, there it is again. Oh, it's all miraged. Huh, it's all distorted. Sometimes you see it, sometimes you don't. The default is to see it, though. That's the point. The default is minus distorting atmospheric conditions, you would be able to see everything clearly. But due to different temperature variations and density in the atmosphere and whatnot, sometimes you can see the whole shoreline and the buildings, sometimes you can't. But the magic trick is not in being able to see it. It's what is taking place that obscures your ability to do so. Look at this. And the mountains in the background shrink and expand and everything too. I would suggest that you hit pause on this video and rewind and watch that back and forth a few times. In fact, I'll put the link in the show notes below, because I sped this up. I made it only 2 minutes long instead of 4 minutes long. So you can watch the whole thing in a little bit slower motion there. But look at the comparison right here, just in these two images right here. The one on the right at 5:44 p.m., 63.5 degrees Fahrenheit. Can't really see anything on the left shoreline there. And on the left at 9:43 a.m., when it was 59.5 degrees Fahrenheit, we can see the shoreline, we can see buildings, trees, all kinds of stuff. So, either this lake is, filling up and draining so that the water level is higher or lower, or it's due to atmospheric lensing and distortions, refraction, and all that good stuff, causing us to not be able to see it at certain times. I think that's exactly what's going on Lake Michigan. And again, based on that imagery that I saw looking 46 miles across versus 0.6 miles across, I really do believe that, just like the experts said, the globalist guys, these are the people who believe in the globe now, they are the ones that said, hey, the atmosphere really is acting like a lens, and they put a lens in front of the camera to show how it works. So I'm just doing what they're doing. I'm using the same logic that they're using, the same science that they're using. And, science is all about testable, observable, and repeatable data, right? So to alleviate the problem of distorting the edges because the magnifying glass ring is too small, I went on Amazon and I got these plastic magnifying sheets and came up with another way of doing the same thing using the sheet right here. Set the city up, a little cutout of the city, and now I've got the big magnifying glass sheet. Bring the camera right up to the lens. See, that's the normal view of the city. Now let's back up again.
The science is the same of that of a lens. Here's a simple example.
So if you're looking at Chicago here,
The atmosphere really is acting like a lens.
yes.
Atmosphere really is acting like a lens, and this is how much of the city is missing due to the lensing effect, the magnification of the atmosphere. You're missing a good portion of the city just by pulling my iPhone back on a 3-foot long desk. That's how much I lost of the city. And as with any scientific experiment, you always try to improve upon what you did before. So I got some foam core, made a little housing for the magnifying sheet, and pasted the city on the back there, and I made it as two separate pieces so that I could flex it as necessary, because I think that there are different types of atmospheric conditions that would allow for more magnification versus less magnification. So in this scenario you have more magnification, and in this one you have less. And for this one I decided to put the Toronto skyline into my little box here. And let's try it again. Okay, we're all the way up against the glass. Now let's zoom across the lake. And wow, look at that. The lower portions start to disappear. Now let's zoom back in to get a little closer to the one that Captain Baltard was talking about here. And wow, look at this. Here's his image on the right, and here's my image on the left. Missing the lower portions of the city had nothing to do with curvature whatsoever. And this, of course, is my answer to the meme that you've all seen being passed around on Facebook showing the missing part of buildings is absolute proof of the curve. No, not really. But as I got to thinking more and more about all this stuff, I realized you may not even need the lensing, atmospheric refraction, and all that either. For example, just go out into a field, something like this. This is a nice flat field out by my apartment complex. Lower your iPhone to the ground to simulate us, because we're really small on this massively large plane, right? Straight horizontal plane. Then go ahead and walk away from your camera on this flat horizontal plane. And just for the fun of it, let's go ahead and bring the city in here. And I'll try to keep my head right between those two buildings right there. And I'm going to pull the city along on this flat, straight, horizontal plane, pulling the city far away, and just simply due to perspective lines, look at what we end up with, boys and girls. Amazing, isn't it? Now let's bring the water line in to simulate water instead of grass and get rid of the background there with some sky. Now let's slide our little city over here, put the big city back in, and well, just due to perspective lines, this is how much of the city magically disappeared. So based on what we've just seen here, apparently all you either need is atmospheric magnification, refraction, or perspective lines. Either one or all three can easily account for the obscuring of the lower parts of cities and ships for that matter, with no need of curvature whatsoever. And I'm going to talk a lot more about perspective, because I do believe perspective is also playing a major role in all this, and how our eyeball works and how lenses work in general, and visual acuity and all that kind of stuff. So I'll save that for part 2. But just as sort of a bonus round to close this video off, if perspective works for ships and for cities, I guess it would work the same for the sun too. So maybe this explains sunrise and sunset on the flat Earth. Works the same way. Perspective. Pretending my face is the sun, face like the sun. Little shout out to my friend Gons. There you go. It's not rocket science. I'm sure by now most of you have probably seen this little animation I created. This was done actually back in May of 2015, so it was a month after I first got into this, when I was kind of considering all of it and going, well, I wonder how that would work. And so I created a little animation in Poser, created a point light with a limited throw ratio, so the light is limited as far as how far it'll go, and just animated it in a circle over the circular flat Earth map. Now, let me just say, neither one of these are to scale. I was just going for the concept here. According to Zetetic Astronomy and other resources, people looking at the sun and gauging its size and distance using a sextant, apparently the sun would be just shy of about 40 miles across and roughly 3,000 miles high. So obviously that's not being depicted here. That scale's not accurate, and it would go in and out on the various tropics and of course the equator. For more information on that, see my animation to the right there. It says how the 4 seasons work on the flat Earth model. Check that one out, and also you might want to listen to the radio show that I did with Zen Garcia, who's done some amazing work in tying all of this into the Book of Enoch and how Enoch describes the various motions of the heavenly luminaries. Lots of good stuff there. But of course, the critics look at this and they say stuff like,
If the sun and moon were just circling over the flat Earth and getting too far away to see, then we would see them shrink and fade out of view as they set. But we don't. Flat Earthers will show you videos where the sun appears to grow or shrink, but this is an illusion due to thick clouds. You can always see that there are clouds near the horizon when they try to show this. Normally, this illusion does not happen.
Oh, so he said that flat earthers are always hiding it behind clouds or whatever. Well, there's plenty of footage out there you can find where there's no clouds involved. This is from a really good video online you guys need to check out called Flat Earth Proof Sunset off Phuket. I'm not sure if that's exactly how you pronounce it. Phuket. Really interesting, showing sunset up. I believe this was actually somewhere off the equator. Again, you'd have to watch that video for yourself, but it clearly shows the sun changing in diameter as it goes away. So please take note not to ignore this evidence. Other videos you've seen where it looks like it's going in an arc like that and going off into the distance. Other videos where people have taken and used filters and whatnot and analyzed the sun moving and then done measurement of pixels across the screen, showing that it does in fact look like it gets a little bit smaller in some cases. In some cases it gets a lot smaller. In this case from 302 pixels to 290. And then of course there's this video right here, which apparently was shot in the desert where there's going to be a lot less moisture. And so whenever there's less moisture, you're going to obviously have less refraction and magnification.
You don't get to pick the anomalies that seem to agree with your views and ignore the common observations that don't, and still call yourself an honest investigator. That is intellectually dishonest.
So thinking about all this and thinking about what I had just shown you regarding atmospheric lensing, magnification, refraction, all that with regard to cities and objects at a distance on the land, I got to thinking, I wonder how this would work with the sun and moon. So this is what I came up with. I've got my magnifying sheet frame, and I created a little stand to paste the sun on it and keep it the same height over the flat surface of a table. So the sun is always going to be parallel with the surface. And check this out. All right, here's the first test of a sun moving over a flat surface, and with no atmospheric magnification, it does what we might expect it would. It gets smaller as it goes away from us. All right, now let's see what happens when we add in our atmospheric magnification. Again, water and refraction. Water causes magnification and refraction, right? So let's bring the sun back. Oh, check this out. Refraction bends the light downward. It made the sun set on a parallel surface. As it was moving parallel, the same height, the whole way over a flat surface, the refraction caused the sun to set. Not only that, well, let's bring in the beginning of that little test, and we see that it maintained pretty much the same size, too. Pretty close. And of course, that's because as it's moving away, the magnification is still taking place. And so even though the sun's further away than it was in the beginning of the test, the magnification basically preserved the same size, and the refraction made it set. Of course, again, depending on how much moisture is in the air, we could see that the sun doesn't appear to change in size at all as it goes down. We could see sometimes perhaps that it looks like it's getting bigger when it goes down. You ever see like a really big sunset or moon rise, moon set, where one of them looks really large on the horizon? Well, that could be because there's lots of moisture in the air causing that effect. Or when there's less moisture in the air, obviously you won't have as much magnification taking place, and so it looks smaller as it goes away. So it's all relative to the amount of moisture that's in the air. Now, I'm just going to put forward a crazy idea for you to think about. And that is, if Rob Skiba could figure this out, I'm just going to go out on a limb here. I think it's quite possible that the creator of the cosmos could have figured out the same thing and engineered our beautiful sunsets, thanks to all that water he placed in our atmosphere. Just something to think about. Thanks so much for watching. I hope you enjoyed this video presentation. If you did, please subscribe to my YouTube channel, like the video, and share it on your favorite social media sites. There's a lot more to come, so stay tuned and we'll see you back next time.